Good day and welcome back. This is our first video discussing partial derivatives. So we have finally made it to this topic of differentiation. And our goal is to kind of introduce the concept of what we call these partial derivatives, which allow us to differentiate functions of multiple variables. And a good starting point is just to remind ourselves kind of how we went about this in Calculus 1. For a function of a single variable, we say it is differentiable at a value x equals a if, in the notation we use, recall as f prime of a, is the limit as h approaches 0 of the difference quotient, f of a plus h minus f of a over h, exists. And we are now ready to extend this idea to differentiate a function of two variables with respect to either variable. So a partial derivative with respect to x, or a partial derivative with respect to y. In terms of a technical definition, we will define the partial f sub x to be equal to, and this is going to be a derivative in the x direction. So we're going to take the limit as h approaches 0 of f of x plus h comma y minus f of xy all divided by h. And the idea is that what we're really doing is kind of fixing that y value and then seeing what happens as we change in the x direction. This is what we call a partial derivative with respect to x. And don't be too concerned about seeing this limit definition and the fact that it looks abstract, because it is something we will very rarely go back to, and in fact we will very quickly make this nice and concrete by working through some examples. But similarly, let me go ahead and write down how it is we can think about the partial with respect to y. Similarly, this would be the limit as h approaches 0 of f of x comma y plus h minus f of xy over h. And I do want to make a few observations, the first of which is purely in terms of notation, and I'm going to write it down in terms of x's, but it also works just as fine for the partial with respect to y. So we may write f sub x of x comma y, and in words I would read the partial derivative of f with respect to x. Oftentimes we might, depending upon what is convenient, drop the x comma y and just write f sub x as the partial of f with respect to x. And instead of saying df dx, when it is a partial derivative to make sure we're distinguishing between the two, we would use this fancier script d, and I would read this partial f over partial x. And when appropriate, we will even sometimes represent this as d sub x, which indicates take the derivative with respect to x. And the notation is similar for that partial with respect to x. And in this video, we will focus in on thinking about the partial derivative from the computational perspective. And in the next video in this series, we'll really dive into kind of that more geometric interpretation. How can we visualize the partial derivative? So in terms of working towards a computation, let me kind of write down in words how we go about this, and it will give us all of the intuition that we need. So to find a partial f sub x, what we do is we treat the y value in a sense as being fixed, i.e. a constant, and then we're really differentiating in that x direction. So to find y sub x, treat y as a constant, and differentiate with respect to x. And note the exact same thing is true for the partial f sub y. To find f sub y, we now treat that opposite variable x as a constant, and we differentiate with respect to y. And before diving into our two examples that we see, I also want to note that all of our old rules of differentiation apply. So all old rules of differentiation apply. And what I'm getting at here is all of these things we've spent so much time working on in the past, we're going to be able to reuse. So things like the product rule, quotient rule, chain rule, even implicit differentiation. So let's go ahead and make these ideas a bit more concrete. So for the function f of xy defined as y squared x plus x squared, let's just computationally determine what is the partial with respect to x and what is the partial with respect to y. For the partial with respect to x, remember our approach. Any y, so here it's a y squared, we treat as a constant. And then we differentiate with respect to x. So if y squared is a constant, we would have the derivative of a constant x, which would be that constant, plus the derivative with respect to x of x squared, which is 2x. So once again, to find the partial with respect to x, we treat each and every y, here it's the y squared, as a constant, and we differentiate with respect to x. Similarly, if I'd like to find f sub y, what we are going to do is treat our x values now as constants. So we think of x and x squared as being constants. So we have the derivative of y squared times a constant, which would be 2y multiplied by that constant, plus the derivative of x squared with respect to y. And note, you do not need to write down 0. That's simply to just help illustrate that this x squared became 0 when we differentiate it with respect to y. And as is usually the case, this is a type of thing that the more examples we work through in practice, the more efficient and also the more natural it becomes. So let's go ahead and do the same thing now for this function g. And the observation is that to differentiate g, it's a fraction, we need to apply the quotient rule. And I'm going to write out a few more details than you might write out, but it's definitely worth doing in this first example. So if we calculate that partial with respect to x, we're going to apply the quotient rule. The quotient rule tells us in words low d high, and when we differentiate the top, that's with respect to x, minus high d low, once again with respect to x, all divided by the bottom squared. And now that we've written out the quotient rule, it really breaks it down into these two simpler partial derivatives that we can evaluate. Note the partial derivative with respect to x of that first term in the numerator is 1. The partial derivative with respect to x of the second term in the numerator is also 1, because in either case we treat the minus y or the plus y as a constant, and the derivative of a constant is 0. So putting this all together, we would have x plus y times 1 minus x minus y times 1, all divided by x plus y squared. And if we go ahead and distribute that minus sign through in the second term, we have an x minus x along with a y plus y. And we end up with 2y all divided by x plus y squared. And we can go ahead and do essentially the same thing with the partial with respect to y. So if you want to calculate the partial with respect to y, you would once again use a quotient rule. And the quotient rule tells you low d high, and that's a partial with respect to y, minus high d low, once again with respect to y, all divided by low squared. That partial with respect to y in the first term is a minus 1 because we treat the x as a constant, and similarly a positive 1 in the second term. And I'll let you do the small amount of simplification required here, but you essentially have in the top from left to right minus x minus y minus x plus y. So the y's cancel, and we're now left with a minus 2x over x plus y quantity squared. We are going to move on to one more computational example in just a moment, but before doing so, I do want to make an observation to kind of lead us into our next topic. That is, now that we have these derivatives computationally, how can we interpret it? So for example, we note that if we take this partial with respect to x and plug in a specific point, say 2, 1, what we are going to get back from this is 2 times 1 over 2 plus 1 quantity squared, which is 2/9. And the question that we want to answer in our next video is going to be, what does this number tell us? That is, what is maybe the geometric or even just the physical significance of this number 2/9? But we're going to have to hold on for one more example. Just to get some more practice with the partial derivative, I have the function arctangent of x square root of t. I would like you all to pause your video and take, let's say, 2 or so minutes and see if you can calculate out these partial derivatives. And assuming that you've paused your video and you've done a few computations, let's go ahead and get some details written down. For the partial with respect to x, or in a moment the partial with respect to y, we approach this in the exact same way. Note that we have arctangent of x square root of t, and that of in there indicates that we have a composition, so we are going to need to use the chain rule to get started. So the partial with respect to x, we take the derivative of arctangent, 1 over 1 plus something squared. We substitute in that inside function, and then we multiply by the derivative of the inside function. And when we calculate the partial of the inside function with respect to x, we have x times the constant square root t. The derivative of x times a constant is simply that constant. So square root t over 1 plus x square root t squared. Similarly, if we want to calculate the partial with respect to y, we apply the chain rule. The derivative of the outside, evaluated at the inside, multiplied by the derivative of the inside. And in this case, when we differentiate the inside function, we're now treating the x as a constant, while we differentiate with respect to t. And recall, the derivative of the square root is 1 over 2 square roots of t in this case, all divided by 1 plus x square root t quantity squared. And I do realize that there is most definitely simplifications that could occur in either of these, but in terms of working with the partial derivative, getting a formula that represents them, I am okay leaving it at this point. In the next video, we'll move on to discuss the interpretations of the partial derivative. So stay tuned and take care.